Okay, we'll go ahead and get started. Can everyone hear me okay and see the slides?
Yep.
Okay, thanks. So what we're going to do today is we're going to finish up the lecture on chapter 7. And then on Wednesday, we'll start on chapter 8. And we'll also have a quiz. And the quiz will cover chapter 7. So finish chapter 7 today. Wednesday, first half of the class, we'll start chapter 8. And second half of the class will be a quiz on chapter 7. The other thing I wanted to mention is that this week in lab is makeup week. And so if you've missed a lab, it's your opportunity to make the lab up. If you didn't miss any, that's great. Congratulations. And you'll get the week off. Then next week during your lab period, you'll have the final exam. So this will be a comprehensive final exam over all of the labs that we did this semester. It's a closed book, no cell phone, no computer, and lab final, and you will take it, unless your instructor tells you otherwise, you'll take it in the computer room that we've been in the last 3 weeks. So come to class at the beginning of the lab period, and then that room's big enough that the whole section can take the test at once.
I have a question.
Mm-hmm.
Okay, so it's over all the labs we've done, or it'll be like a specific thing?
Yeah, it'll cover all the labs that we did this semester. So it could be calculations associated with any of the labs. It could be associated with theory that we talked about in the labs. It's basically trying to determine, hopefully what you learned in those different labs that we did.
Okay, thank you.
Mm-hmm. Any other questions about the final?
Do we know how many questions it is yet?
No, I haven't made it yet. It's 100 points, but since I haven't written the exam yet, I don't know how many questions.
And is it going to be multiple choice like the exams that we have
No,
in class?
it will not be.
Okay.
So one of the nice things about this is that with the exams we've been having, since they're taken remotely, it's a little more difficult to have students write out answers and things like that. So one nice thing about this is it's an opportunity to get away from the multiple choice, which you can think if that's good or bad, but I think it's good because it allows partial credit to be a possibility on some of the calculations. Whereas now it's kind of you either get it right or you get it wrong.
Are we allowed to have our calculators? Or
yes, you will need calculators. So definitely bring your calculator. You will need that. But as I said before, it will be closed book. So you won't be able to look at your notes or anything like that, or Google stuff, or.
Will there be some type of like study guide or anything?
Nope.
Okay, just wondering. And I had another question, but I can't remember. So I'll get back on that.
Okay. All right. So as I said, today what I'd like to do is to go ahead and finish up chapter 7 in preparation for the quiz on Wednesday. So I'm going to go back and repeat a couple of things that we talked about last class. One is I just wanted to talk about effective nuclear charge again. And if you remember, there were 2 ways that we calculated that. One was the formula that you see on this slide, which is that the effective nuclear charge is the atomic number minus the screening constant. And the simplest way to calculate that screening constant is to just count up the number of inner electrons. If you recall, we also had another way to calculate that screening constant, and that centered around Slater's rules. And if we calculate that effective nuclear charge, nuclear charge using Slater's rules to calculate the screening constant, I wanted to review those rules. And remember, this is used for elements that do not have D or F subshells. So the screening constant in this case, the rules tell us that electrons for which the principal quantum number is larger than the value of n for the electron that we're trying to calculate, that contribution is 0. So in other words, if you have, let's say, a 2s electron you're trying to calculate, and there's a 3s electron present, that 3s electron, because it's at a higher energy level, won't do any screening, and so it doesn't impact the effective nuclear charge. The other thing I want you to remember is when we say n, we're talking about that principal quantum number, and that principal quantum number, when we say 2s or 2p or something like that, it's the number in front of the letter. That's the principal quantum number. So if that value of n, the value of the principal quantum number, is the same as the electron we're calculating this for, if it's the same, then we have a contribution of 0.35. So we would multiply that number of electrons by 0.35. For the electrons that have a principal quantum number of n minus 1, those contribute 0.85. And then electrons that have a smaller than n minus 1 value contribute a value of 1. So basically what it's telling us is the closer the electrons are to the nucleus, the higher the contribution to that shielding constant. I'd like to go ahead and go through the fluorine example that we talked about. In fluorine, we have 9 total electrons. And if we look at them, we see that we have 2 1s electrons, 2 2s electrons, and 5 2p electrons. So if we were going to calculate shielding factor for one of the valence electrons, then we would look at and see that we have 7 electrons with an n equals 2. So in other words, in that outer shell, that highest energy level, we have 7 electrons, 2 2s and 5 2p. Going back to our Slater's rules, we see that electrons with the same value of n as the electron interest contribute 0.35. Since we don't count the electron that we're studying, instead of having 7, we would have 6 valence electrons. And so that would be times the 0.35. Then once again, going back to our rules of electrons with a value of n minus 1 contribute 0.85. Well, n is 2, so n minus 1 would be 1. So we have 2 of those electrons. We have 2 1s electrons. So that would be 2 times 0.85. So we sum that up and we get a value of 3.8. And so 9 minus 3.8 is 5.2. So a little bit different when we have the Slater's rules in use than when we don't. But I wanted to review that, and let's just go through, one of these Slater rules, another example here. So if you get a question where you're asked to calculate out Z effective using Slater's rules, the first thing you want to do, and let's take this sodium as the example, you want to write out the electron configuration. So in this case, the electron configuration is 1s2, 2s2, 2p6, and 3s1. So applying our Slater's rules, first we look to see how many electrons are in the shell that has the quantum number that we're interested in. So 3 is the highest quantum number. So we see what we have in the 3, n equals 3 level. And we have 1 electron at 3s1. So we don't count that electron that we're studying. And since there's no other electrons at the n equals 3 level, that 0.35 would be times 0. So there's no contribution there. We then look at n minus 1, and that's the 0.85 factor. And we add, in this case, we're at n of 3, so n minus 1 would be 2. So we look at the 2s level and the 2p level. We see we have 2 electrons at 2s, and we have 6 electrons at 2p. So a total of 8 electrons there. So we have 0.85 times 8 to get that contribution. And then finally, we look at the lower levels. And so in this case, we have a 1s level, and we have 2 electrons there. So we would have 1, which is the factor, the Slater factor for that level, times the number of electrons, which is 2. So we'd sum all that up, and we get a value of 8.8 for the shielding factor, and we would have 11 minus 8.8 would give us 2.2. If you went and did potassium, which is the next one, you'd have a similar type of approach. Any questions on using the Slater rules to do this shielding calculation? Okay. Remember, we talked about ionization energy. And the important thing about ionization energy is that that's the amount of energy required to remove an electron from the ground state of a gaseous atom or ion. So the smaller the ionization energy, the easier it is to remove that electron. The other kind of compatible thing that we talked about was electron affinity. So ionization energy is losing electrons. Electron affinity is the energy change when something gains an electron. So if something loses an electron, you're going to be left with a positively charged ion, a cation. If something gains an electron, then you're going to be left with a negatively charged ion or an anion. So both of these are real important, because when we think about forming these gas phase ions, whether it be a cation or an anion, understand electron affinity values or ionization energy values tells us how easy or how difficult it is to do that. I think I'd mentioned before that this kind of gas phase ionization chemistry is real prevalent in mass spectrometry. And so it's a pretty big deal in the world of analytical chemistry to do analysis, especially low-level selective analysis of things. So the homework, I'm not going to go through the homework on this because I think it's as you go through it, you know, the answers, there's not really calculations in that. It's just kind of picking out trends and things like that. So please spend some time reviewing the homework on this. And so now let's go and talk about metals, nonmetals, and metalloids. When we think back, when we talked about the periodic table a while back, early on, we said that if we look at the periodic table, the elements that are over to the right in the upper right-hand corner, those are our nonmetals. We said all the things on the left-hand side, those are the metals. And then if we look at this periodic table and see the dark line that kind of starts between boron and aluminum, kind of over towards the right, and is like a stair-step dark line, that was the line that said things along this tend to be metalloids. And so that would be boron, silicon, some things like that, the ones that are slightly different, kind of purplish color there. So another thing I want to point out is if we look at the arrow at the top, we see that as you go from right to left, on the periodic table, you increase the metallic character. Now, the exception to that is hydrogen, and we'll talk about hydrogen in a little more detail later in class, but let's not count hydrogen in this discussion for now. But if you look at the other ones, the kind of light purplish ones, those are all the metals, and as we go from right to left, we increase metallic character. We also increase the metallic character as we go from top to bottom in one of these columns. And so what we see is lower left-hand corner, those would be the increasing metallic character, and upper right-hand would be lesser metallic character for the metals. So when we think about the differences between metals and nonmetals, there are two key things that come out. One is the metals usually form cations. And so here you see some metals listed in blue. And like I said, we'll talk about hydrogen a little later, but you see these metals in blue, and we see that they're all positively charged. The nonmetals tend to form they're anions. And so the pink ones on the right, you see all of those are anions, negatively charged. And so if the metals are forming cations, that means they want to donate electrons, they want to give up electrons. Because remember, if you lose negative charge, then you wind up being resultant ion is a positively charged or cation. The nonmetals like to pick up electrons. And so because they're adding negative charge, those ions will be negatively charged. So it's kind of like a match made in heaven, this metal nonmetal thing, because you have some that like to give up electrons, the metals. You have some elements that like to pick up electrons, and that's the nonmetals. When we talk about metals, most of the elements in nature are metals. And so we go back to the periodic table here, and we look at the number of things that are in pink, and those are our metals. And you see there's a lot more of those than there are nonmetals or metalloids. So there's a lot of them, but if you look at the nonmetals, we have things like carbon, nitrogen, oxygen. So even though there's fewer nonmetals, there's a lot of carbon in the world, a lot of nitrogen, a lot of oxygen. So a lot of these metals, there's a lot of them, but their quantities aren't that great. Some general properties of metals, they tend to be shiny. And the other thing, though, which is a little more practical, is they conduct heat and electricity. They're also malleable, which means you can kind of shape them and they don't break, bend them around. They're ductile, which means they're pliable. So this ability to kind of shape and work with metals is a big benefit of them. And then they're usually solids at room temperature. One notable exception is mercury. That's a pretty dense liquid. And they have low ionization energies. Remember, we said the metals like to form cations, and that means that they're going to give up electrons. And so that goes back to what we talked about earlier, that ionization energies are a reflection of how easily something gives up an electron. So low ionization energy means that you can form the cation relatively easy. Just talking a little bit about that ability to shape the metals, the one thing, and also the conducting of electricity. I always think of the wiring, electrical wiring, the copper wiring, for instance, is that you think about that wiring, it can be made into thin wires. That thin wire then can be bent and things like that, and it usually doesn't break. And so that still keeps its ability to conduct electricity through the wire. So some general properties that you see with metals. We'll talk a little bit about metal chemistry. So compounds between metals and nonmetals that are formed usually are ionic. And so this gets back to that metals being cations, nonmetals will be anions. So there's a nice match there. And metal oxides tend to be basic and they react with acids. We'll go through some of these example reactions a little bit later when we look at some of the homework problems. Nonmetals, as we said, are found on that upper right-hand side of the periodic table, and their properties are different than what we see with the metals. We said the metals are almost always solids. Well, the nonmetals can be solids, liquids, gases. It kind of depends on which element you're talking about. They're not shiny. The metals tend to be shiny, bright, shiny. The nonmetals are not. And the other things is that they're brittle. So you can't really work with them as easy as you can the metals. And the other thing is they're poor conductors of electricity. So kind of the opposite in terms of physical properties for nonmetals than you have with metals. We talked about how the nonmetals like to form anions. So since they like to form anions, that tells us that they must have a large negative electron affinity. So in other words, they really like to pick up those electrons. Because they have that electron affinity, they can form the anions easily. So metals, nonmetals, pretty much opposites of each other. When we talk about substances that contain only nonmetals, and this is usually what you're talking about when you're talking about organic compounds. So the field of organic chemistry, compounds that contain carbon, hydrogen, nitrogen, oxygen, things like that. Those types of compounds that contain only nonmetals, we call molecular compounds. There are nonmetal oxides, and most of those are acidic. So if we just kind of review the differences in the properties of the metals and the nonmetals. So the metals, they tend to be shiny. So in other words, if you were walking along and there were some nonmetals in a rock or something, you might see something that would catch your eye. They can have different colors, but usually they're kind of a silvery color. The nonmetals, you don't have that shiny luster, and there's various colors of those. The metals are something that you can work with from a physical manipulation perspective. So you can make things like wires and things where you can extrude or bend or things like that. The nonmetals, those solids are usually brittle. Some might be harder than others, but usually you're not working with those a lot. The metals are good conductors of both heat and electricity. Nonmetals, just the opposite. They're poor conductors of those things. Most metal oxides are ionic solids that are basic. The nonmetal oxides are molecular substances that form acidic solutions. So once again, pretty different properties there. The metals tend to form cations in water, whereas the anions, the nonmetals rather, will form anions or sometimes oxyanions in aqueous solution. So key takeaways here, metals, easier to work with, good conductors of heat and electricity, tend to form cations. Nonmetals, brittle, not easy to work with, poor conductors of heat and electricity, and tend to form anions. So let's talk about the metalloids for a moment. So metalloids simply are elements that have some characteristics like metals and some characteristics of the nonmetals. So they're kind of in between, a little of both. Where you tend to see those are in computer chips and things like that. So what I'd like to do now is talk about some group trends. And so remember, groups, when we say groups, we're talking about the columns in the periodic table. And so what we see is that the elements in a particular group tend to have similar properties. And there's also tends to be trends within the groups. And so we'll talk about that a little bit. The groups we're going to focus on are Group 1A, the alkali metals, Group 2A, the alkaline earth metals, Group 6A, which is the kind of the oxygen group, Group 7A, the halogens, Group 8A, the noble gases, and then we'll talk a little bit about hydrogen. And so hydrogen is considered a non-metal, but yet it's usually written over in that 1A group. So we'll talk about why that is also. So alkali metals, that's that 1A group. Remember we said group 1A is the alkali metals. So that's 1A, if you recall, is the far left column on the periodic table. So that's sodium, potassium, things like that. And these metals in their metal form tend to be soft and metallic looking. So kind of like a dull grayish with a little bit of can be a little bit of shininess, but usually they're kind of dull gray looking. I'm not certain which metal that is they're cutting there, but a lot of these metals look the same. They have that same kind of look. They also tend to be very easy to cut. So you can typically cut these with like a butter knife or something, which is kind of odd. That's a really big chunk of whatever that is there. They are found in compounds in nature, not in their elemental forms. So you're not going to walk around and find a chunk of sodium or potassium there, although those can be made and isolated from the compounds. And we'll talk about the metallic form, their elemental form in a little bit. So typical properties is they're good conductors, things like that. They also tend to have low densities and melting points, and they have low ionization energies. So in other words, if they have low ionization energies, it's pretty easy to form a cation. And so a few things I want to point out. So we've got some of them listed here: lithium, sodium, potassium, all the way down the line. And let's take a look at their electron configuration. What we see in that 1A group is that we have our noble gas core electrons. So the noble gas will vary depending upon which level it's at. And then we have the valence electrons. And in each case, the valence electrons, there's only one of them, and it's a shell, an S shell electron. So whether it's 2s, 3s, 4s, 5s, 6s, we have one electron, one S electron there in that outer shell. If you think about it, these alkali metals, that 1A group, typically have a +1 charge. And so if we look at their electron configuration, we see there's just that one valence electron, that one S electron. So it's pretty easy for the element to lose that electron, donate that electron, and then be left with a +1 charge. If we look at the melting points, we see the melting point decreases as we go down the group. And we see density increases. We also see the atomic radius increases as we go down to group 1A. And we can think of that as, if we look at the electron configurations again, we see cesium, our principal quantum number is 6 on that 6s electron. So that's telling us we've got a lot more space that we've taken up as we've added these different orbitals, versus lithium, which its outer electron is just a 2s. So that 2s energy level is quite a bit lower than the 6s. And then finally, we see the ionization energy, a little bit of a trend as you go down. We see it decreasing, but all of those are pretty easily ionized, whether it's 520 or 376. I mentioned a little bit about the reactivity of these, in this case, lithium, sodium, potassium, in their elemental form. So if you do get one of these in its elemental form, if you put it in water, it basically explodes. And so these are some pictures of where someone must have taken a little bit of it and put it in water. And so they're really very exothermic reactions. So you get like a flame, and if you throw it in some water, a lot of times you'll hear a popping sound, kind of like a firecracker, depending upon how much it is and things like that. So the alkali metals sometimes are used as catalysts, and so in that case, you just have to make sure your solvent is on water, or you'll get this pretty violent reaction with water. So let's talk a little bit about some differences in alkali metal chemistry. So lithium, if you react that with oxygen, you make an oxide. So in other words, lithium plus O2 gives us lithium oxide. Sodium reacted with oxygen, and so this is oxygen gas. It forms a peroxide. Potassium, rubidium, and cesium, they form what we call our superoxides. So superoxide is the O2 minus ion. And so in that designation where it says M plus O2 goes to MO2, the M is just a shorthand for either potassium, rubidium, or cesium. So rather than writing all three out, just the M says any one of those will react this way with oxygen. So this type of understanding of these different alkali metals react with oxygen a little differently would be something that you would be expected to know. Another interesting thing about these alkali metals is that you can do a flame test, and that can tell you which metal it is. And so this used to be a pretty common Gen Chem experiment, and I'm not certain how much it's done anymore because you have a lot of flames going on and people burning stuff in that. And so I think for safety reasons, it's probably done less than it used to be. We don't do it here. But what you're seeing is that for each of these elements, if you put them in a flame, you have enough energy to have the electron go from the ground state to an excited state. And this kind of goes back to when we talked about quanta of energy and photons and all that. So you put the right amount of energy in, and you get that electronic transition from a ground state to an excited state. In this example, they're showing an electron going from the 3s to the 3p level. And then when it comes back down from that excited state, in this case, once again, from 3p to 3s, a photon of that energy is emitted. So as you excite any of these, if you have the right energy in to be able to go from that ground state to an excited state, as it comes back down from the excited state to the ground state, it will emit a characteristic wavelength, and that wavelength is one of the visible wavelengths. And so what you see here is, you see for lithium, it's kind of a reddish color, sodium, it's yellow, and potassium is kind of a purplish color. So if you were to have a compound that had one of these in it and you put it into the flame, you would see this color, and that would allow you to tell if it was a lithium salt or a sodium salt or a potassium salt. Let's go on to the alkaline earth metals. So that's the 2A group. So the alkaline earth is the 2A group, and here's some examples of those metals. So magnesium, calcium, barium, things like that. When we look at their electronic structure, electron configuration, we see that we have that core electrons based on the noble gas that's closest to it. And then we have the valence electrons. Just as the alkali compounds had one s electron as its valence electron, the alkaline earth has two s electrons as its valence electrons. So that's the thing it has in common. Similar to losing that one electron is what the alkali metals like to do. The alkaline earth likes to lose two electrons. So we have these two s electrons as its valence electrons. It's pretty easy to lose those electrons, and that leaves us with a cation in each case, and it's a cation with a +2 charge. So fairly easy to ionize. We look at these numbers ranging from about 900 to 500. The alkali are still a little bit easier in terms of ionization numbers, but both of them ionize pretty well. We kind of see a little bit of trending on melting point, not as clear as some others. Density, a little bit of trending there as well. And then finally, the radius, we see that increasing just as we saw with alkali as we get to those higher energy levels. So in other words, the principal quantum number increasing. When we talk about some reactions, we see beryllium doesn't react with water. So we go back here and we see beryllium's the first one, then magnesium. Beryllium doesn't react with water. Magnesium reacts with it only when the water's in the vapor phase, in other words, steam. But then the other alkaline earth metals react readily with water. So what that's telling us as we go down this group, down this column, we get greater reactivity. Let's talk about group 6A for a second. And so 6A is interesting because 1A and 2A, those were all metal elements. Now we go over to the right side of the periodic table and we look at group 6A. And so that's oxygen, sulfur, selenium, tellurium, polonium. And what we see is in this, because we're kind of crossing that metalloid kind of stair step in the periodic table, we see some of these compounds, or rather some of these elements are nonmetals. We have example that's a metalloid, and we also have a metal. So we have kind of a mix here. And because of that, we see a little bit different in terms of properties. And we also see some differences in electron configuration. So we see oxygen and sulfur, those are kind of similar, where we have the noble gas core. Then we have some s electrons and some p electrons, and those have the same quantum number, 2 for oxygen, 3 for sulfur. But then we get to selenium, and now we've introduced d electrons. And those d electrons, those valence d electrons, have been introduced, and they're not at that 4 level, that n equals 4 level that the s and p electrons are at. They're at the 3 level. In tellurium, we see a similar thing of where we have some 4d electrons, and when we have 5s and 5p electrons in the valence electron group. And finally, polonium is even a little different, more different, because we have f electrons, we have d electrons, in addition to s and p. So we have principal quantum number of 6, that's the s and p electrons, principal quantum number of 5 for the d electrons, and principal quantum number of 4 for the f electrons. So we've got some different n values there in its valence electron configuration. We look at melting point, we see that kind of jumps around. We look at density, we do see the density increasing as we go down the group. We see the radius increasing as we go down the group. And we see the ionization energy decreasing as we go down. So just to remind you that oxygen, sulfur, and selenium are nonmetals. The tellurium is one of the metalloids, and then polonium is a metal. It's radioactive, but it is a metal. When we talk about either donating electrons or picking up electrons, oxygen, that tends to be a -2 charge, an anion, so it likes to pick up electrons. Polonium, on the other hand, usually is most likely to have a positive charge, so it would donate electrons. And so there we see the difference between oxygen being a non-metal, something that likes to pick up electrons, and polonium, metal, something that likes to donate electrons. The other comment I'll make about oxygen is that it's what we call an allotrope. And an allotrope means that there's more than one physical form. And so for oxygen, it can exist in 2 different elemental forms. So oxygen gas, so the stuff we would breathe, is O2. Ozone gas, which is what you hear about in a lot of environmental stuff when people talk about the ozone layer and things like that, that exists as well, and that's it. Its formula is O3. So oxygen can exist in those 2 different elemental forms. Let's take a look at group 7A. So we go to 7A, that's the halogen, so that's fluorine, chlorine, bromine, that group. And so now all of these are non-metals. And so whereas that 6A group, we had a mixture of metals and non-metals, 7A were just non-metals. And we look at those electron configurations and we see some differences there. We see fluorine and chlorine, each of those have S electrons and P electrons. And then bromine has S electrons and P electrons, just as iodine does, but they also have D electrons. And so those D electrons will be at a lower quantum number, principal quantum number, than the S and P electrons. The other thing that we notice is that for each of these, we're 1 electron shy of completing the electron configuration and going to the noble metal configuration. So that tells us that these are most likely going to easily pick up an electron, that it likes to pick up an electron to get to that more stable configuration. And so 7A group elements typically have a -1 charge when we talk about them in compounds. They like to pick up that electron and get their electron configuration filled out. We look at melting points, and we see the melting point increases as you go down the group. We see density increases as well. Then we have atomic radius, that increases, and ionization energy decreases, but they all ionize pretty well. They have a highly negative electron affinity, so usually when you find them in compounds, as I said, they're usually anions. They react directly with metals to form metal halides. Let's look at group A, the noble gases. So sometimes the noble gases are called inert gases because they're usually difficult to ionize and react. It's not impossible, but under normal conditions, you don't get a lot of ionization happening. So their ionization energies are pretty big, as you can see on the far right. It's in the thousands, even for radon at the bottom. And so because of these large ionization energies, to get them to ionize, you have to put a lot of energy in. And that's because they have a full electron configuration. So we look at those electron configurations and we see, for instance, with helium and neon and on down the line, that all the shells are full. So it's a very stable configuration. So it doesn't have any of these do not have a strong desire to either donate or pick up electrons. So they're usually, as I said, they're relatively non-reactive. You can do some things to form ions, but you got to put a lot of energy into them. And they are found as monoatomic gases. So in other words, we talked about oxygen typically being O2 or O3. Helium, neon, things like that are just He, or it's not He2, for instance. So let's talk about hydrogen for a moment. Hydrogen has a 1s1 electron configuration. So it has an electron configuration that's kind of like a metallic configuration. So it fits in with those other group 1a elements, but it's not a metal. And so when we think of acid compounds like HCl, we usually say that it has a H+, but really it's not an ionic situation. It's more of a covalent bond in nature. When you react hydrogen with metals, you can have a hydride ion, anion form. So that hydride ion would be H-, and that can form. So hydrogen is a bit odd because it can have H+, it can have H-. I will say that typically it's H+. These hydrides are kind of an outlier. More often than not, hydrogen is H+. So there's some homework associated with this. What I'd like to do is go over a little bit of this. We talked about that there were some reactions that can occur. And what I'd like to do is go over some examples of these reactions. This will be something that you would be expected to be able to do on the quiz or the exam. So the first one we'll go through is 7.65. So in 7.65, you're asked to write balanced equations for these reactions. So the first reaction is barium oxide plus water. So barium oxide is a metal oxide. And so you would want to know that a metal oxide plus water forms a metal hydroxide. So you'd need to come up with the molecular formula for barium oxide, which is BaO, and then plus the water. Forming the hydroxide is barium, and then 2 OH groups. So you'd need to know the charge on the barium, the charge on the oxygen. We talked about that in terms of the groups that they're in, that barium is +2, oxygen's -2. So we see that barium oxide on the left-hand side of the equation, that balances out. And then when the barium, this metal oxide, this barium oxide forms a metal hydroxide when it's reacted with water, we'd need to remember that barium's +2, need to remember that the hydroxide ion is -1. So you have 1 barium and 2 hydroxide ions to balance that charge out. So BaO plus H2O gives us Ba and then 2 hydroxide groups. The next one is iron 2 oxide plus perchloric acid. So here we're once again having a metal oxide, and instead of reacting with water, it's reacting with an acid. And we know that a metal oxide reacting with an acid gives us the salt of that metal, and then water. So we'd need to be able to write the molecular formula for iron 2 oxide. So the 2 in there tells us that the iron charge is +2. We know that oxygen is usually -2. So we have FeO, and then perchloric acid, HClO4. Perchloric acid was one of those acids that we learned I forget what chapter it was, but it was a while back. So you'd have to remember that that's perchloric acid is HClO4. And then since we're making a salt, this goes back to one of those exchange reactions that we talked about previously. So the iron would then go with the chlorate ion, and then the hydrogen would go with the oxygen. So the hydrogen and oxygen combined for water. The iron going with the chlorate. Remember, chlorate ion is a -1 charge, so ClO4, that's the chlorate ion. That is a -1 charge. The iron, we know, is a +2 charge because we were told that it was iron 2. And so to balance that, the +2 charge on the iron and the -1 charge on the chlorate, we need 2 of those chlorates. And so that's why we have the 2 outside the parentheses around the chlorate. We're not quite done yet. We need to make sure the reaction is balanced. And so we look at the right-hand side of the equation and we see we have 2 chlorines there. But on the left-hand side, we would only have 1 chlorine from the HClO4. By putting a 2 coefficient in front of the perchloric acid, we now balance our chlorine. If we go ahead and check everything else, we see that it all balances. And so our final answer is FeO plus 2 of the perchloric acid going to FeClO4, 2 of those chlorate ions, and then water. So first one, we had to recognize that it was a metal oxide plus water, and that gives us a metal hydroxide. The second one, we needed to recognize that it was a metal oxide plus acid, and that gives us the salt plus water. And in the third one, now we have sulfur trioxide plus water. So sulfur trioxide is SO3, then plus the water. And in this case, it's a non-metal oxide. So sulfur is a non-metal. So a non-metal oxide plus water forms an acid. And so the sulfur trioxide plus water gives us sulfuric acid, H2SO4. We need to remember that SO4 is a -2 charge. Hydrogen's a +1, so that's why we need the 2 hydrogens there. So recognizing non-metal oxide plus water giving us an acid helps us piece together what this reaction looks like. And then the final one, carbon dioxide plus sodium hydroxide. We look at carbon dioxide, we see that it has carbon and oxygen, the oxide, and so we know that it's a non-metal oxide because carbon's a non-metal. Sodium hydroxide, NaOH, that's a base. So we have a non-metal oxide plus a base, kind of similar to the metal oxide plus the acid up in part B that gave us a salt and water. We know that a non-metal oxide plus a base gives us a salt and it gives us water. So in this case, the CO2 plus the NaOH gives us sodium carbonate and plus water. Then we need to balance things out. So carbonate, CO3, that has a -2 charge in that ion, and sodium has a +1 charge for that ion. And we would then need to have 2 of those sodiums to balance out the carbonate -2 charge. We're not quite finished yet because we see that we have 2 sodiums on the right-hand side of the equation, the product side, but we then can balance that sodium by putting a 2 coefficient in front of the NaOH. If we put that 2 coefficient in front of the NaOH, then now we've balanced our nitrogens. We'd go back and check the carbon, the oxygen, the hydrogens, all that, and we would see that everything balances now. So this type of stuff here that we just went over, where you're given 2 things to react with, and then you need to figure out what the molecular formulas are for the reactants, then predict what the product would be and know that molecular formula, be able to write that correctly. The expectation is you'd be able to do that for these types of metals and non-metal reactions. Different classification of reactions. We had the metal oxide plus water going to metal hydroxide. We had metal oxide plus acid going to salt and water. Non-metal oxide plus water forming an acid. Non-metal oxide plus base forming a salt and water. So being able to recognize if something's a non-metal oxide or a metal oxide, things like that. Being able to recognize acids and bases, and then knowing what the products would be from those types of reactions. And then, of course, the final thing, which we've done in the past, is making sure our equations are balanced. So in other words, you have the same number of the different elements on the left-hand side, the reactant side, as you do on the right-hand side, the product side. Any questions about these types of reactions? Okay. So let's look at 769. We have some more reactions here. So in the first one, we have potassium metal plus chlorine gas. And so we go and form potassium chloride. The thing that we had to do here is we had to remember a couple things. One is that when the potassium is a metal and it likes to donate electrons, the chlorine is a non-metal, it likes to pick up electrons. So that tells us that the potassium is going to wind up being a cation, and it's going to be +1 in charge because it's in that 1A group. The chlorine is going to wind up being an anion. It's in that 7A group, and we know that its anion is a -1 charge. And so we have a +1 potassium and a -1 chlorine to form the potassium chloride. And that charge balances, but what didn't balance is the number of chlorines on the right-hand side and on the left-hand side. So in order to balance that, we had to put a 2 in front of the KCl to get our chlorines to balance. So now we have 2 chlorines on the right-hand side and 2 on the left. Unfortunately, now our potassium didn't balance. We had 2, by putting that coefficient of 2 in front of the KCl, that we wound up with 2 potassiums on that right-hand side. So then we needed to put a 2 over on the left-hand side in front of the solid potassium in order to have that balanced. The next one, strontium oxide added to water. So this is one of those metal oxides added to water that we kind of talked about previously. So that gives us strontium hydroxide. Strontium will have a +2 charge. A hydroxide ion, OH, is a -1 charge. So in order to balance that electronically on that molecule, so it's a neutral molecule, we need 2 hydroxide ions to go with the strontium to balance. And in this case, after we do that and write that SR and then in parentheses OH with the 2 subscript, we go and we check our strontium, our oxygen, our hydrogen, everything balances. And so we're okay there. We don't need to do anything of adding coefficients. In C, we have lithium solid plus oxygen gas. So this was one of our examples, I believe, where we showed that it forms lithium oxide. Lithium, we know, because it's a 1A element, wants to be a +1 charge on its ion, and oxygen, we had said, wants to have a -2 charge. So when it forms this compound, if oxygen has a -2 charge and lithium has a +1 charge, then we need 2 lithiums to balance out that -2 charge on the oxygen. When we do that and we go back and check things, now we see that we need 2 oxygens on the right-hand side to balance out the O2, the 2 oxygens from the O2 on the left-hand side, the reactant side. So if we put a 2 in front of that lithium oxide, we now wind up with 2 times 2 is 4 lithium atoms and 2 oxygens. So the oxygens balance, but now we have 4 lithiums on the right, but we don't have 4 on the left. So we have to go and add that 4 coefficient on the front of the left-hand lithium. So that reactant lithium has the 4 coefficient in front to balance out the lithiums on the right-hand side. On D, we have sodium metal reacting with sulfur. And so here we have sodium sulfide being formed. Once again, we know that sodium is one of those 1A elements, and so it's going to have a +1 charge. Sulfur typically is -2. So we have a -2, we have a +1. We need the 2 sodiums there in that molecular formula to wind up with a neutral molecule. Since we have 2 on the right-hand side, 2 sodiums on the right-hand side, we need to go back and look over at our reactant side on the left, and we see that we need to put a 2 coefficient in front of the sodium in order to balance the sodiums out. The sulfur is balanced with 1 on each side, so we're good there. So this type of problem here where you're given, once again, 2 things that are reacting and be able to predict what the reactant product is something you should be able to do just as the previous problems were kind of similar. Okay, let's look at 771. And in here, we're going to talk about alkali metals reacting with hydrogen to form hydrides, and they react with halogens to form halides. So in this case, the calcium plus the fluorine gives us a halide, and then the calcium plus the hydrogen gives us a hydride. So let's talk about those a little bit. We'll write the balance equations, and so we know that calcium plus F2 gives us, calcium is in that 2A group, so we know that that's typically a +2 charge. Fluorine's in that 7A group, that's a -1 charge, so we need 2 of those fluorines to balance out the calcium. Same with the calcium and the H2. This is one of those exceptions, the hydride that we mentioned, where hydrogen actually has a -1 charge. Doesn't happen a lot, but it does happen periodically. So that calcium is +1. We form these hydrides, and so the hydrogen is a -1 charge. To get that to balance, we need 2 of the hydrogens. So if you recall, we had talked about oxidation states of things. And so if it's a solid, in this case, calcium solid, the oxidation state in that solid form is 0. When it goes over and forms either the halide, in this case, calcium fluoride, or hydride, calcium hydride, then that calcium oxidation state goes from 0 to +2. And so that's how we knew to balance things out with the 2 either F's or 2 H's in these cases. So because the calcium goes, excuse me, goes from an oxidation state of 0 to +2, in other words, it's lost 2 electrons, we know that it's been oxidized. So oxidized means that oxidation number has increased, 0 to +2. The fluorine and hydrogen, those are reduced. So those gained electrons. So now they go from 0 to -1 in each case. So they picked up an electron. So and their oxidation number, Oxidation state went from 0 to 1, to -1 rather. So they were reduced. So once again, something that we learned in the past, these oxidation numbers come back to being helpful to understanding how these reactions go. So don't forget how to do those oxidation states, and seeing how the oxidation states change from a reactant to then whatever the product is formed. So that's it for what I wanted to talk about today. Or does anyone have any questions? Okay, if we don't have any questions, then just a reminder, this week in lab is makeup week. So if you have something to make up, work with your instructor to do that. Next week is the final exam in the lab. And then in the class, Wednesday, we'll start on chapter 8. And then about halfway through the class or so, we'll stop and we'll take the quiz. And the quiz covers chapter 7.
Hey, Professor, I have a question.
Yes.
Can you hear me?
Yes.
It's just like, it's not over computer labs, right? It's just our actual labs, not
It'll be
computer labs.
computer as well. Yeah, there will be some questions from the 3 computer labs as well.
Okay.
So the lab final, anything on any of the labs that we did, I think we did 10 labs total. So anything that was on any of those is fair game. Any other questions? Okay, thank you.